All right, line A6, learning task number 4. We're going to be taking a look at SCR triggering inside of an AC type of circuit. So basically what we're going to be building is we're going to be building dimmers. And the very first one that we take a look at over here is going to go and be this system that we have over here. A couple of things that I just want to identify straight off the bat. This diode that I'm going to go and have over here is simply in there to go and prevent me from having a reverse value of voltage applied to that gate. Remember that these things can easily be damaged, the SCRs, if we have got a opposite value of voltage that's going to be applied to the gate. So that one's in there just simply for protection. The rest of the components that we see inside of here, this is going to go and take care of the actual load control. And then this is going to go and take care of the control triggering. We are going to go and make this resistor over here our ultimate trigger for this thing. And you'll see that it's got an arrow through it, meaning that this is going to be a variable type of resistor. They give us values inside of the book over here for this circuit. And one of the values they give us is that this is going to be a 20k ohm variable resistor, which means that at its max, this thing is going to be 20k ohms, and I can go and drop this thing from 20k all the way down to 0 ohms. That's the way these variable resistors or rheostats work. The other thing that they go and give us is that we need to go and have a minimum amount of I gate, or the total amount of gate current, to go and put this thing into conduction. Once we hit that, then we are going to be fine as long as we still have got our minimum amount of holding current traveling through the main channel. But we only need for a brief instant a small amount of gate current, and they give us this value as being 10 milliamperes. Remember that this is all taking place over top of an AC supply of 120 volts, which is going to be our North American standard, and we are going to go and have a waveform that looks like this. That waveform has got two things we need to note. First of all, there's going to be a part of the waveform when we're in the positive, and there's going to be a part of the waveform that we are going to go and be in the negative. Our SCR is going to be a directional device, which means that that SCR over there is only going to go and conduct for half of those. It's either going to pick the positive or the negative depending upon its orientation. We'll pick the positive for this one, and we will say that the other half is going to go and get scratched out. We're going to be blocking for that one over there. The other thing is that 120 volts is going to go and be a RMS value of voltage. And if I want to go and convert from 120 volts RMS to find out what my actual value of peak voltage is, it's going to be all the way from 0 up to what we call a peak value of voltage. And to find that, we just go and take our RMS voltage, RMS, divided by 0.707, which is going to go and give us our V peak. So we're going to do that real quick. We're going to go and take 120 volts divided by 0.707, which is going to go and bring us out to a peak value of 170 volts. Roughly, it's 169.7. We're just going to round that off, and we're going to go and call that peak over here 170 volts. Okay, so we can scratch all this out of the way so that we've got room to write. And now let's go and take a look at what happens. First of all, if we are at a complete pile of resistance inside here, so I've got my full 20k ohms across here, then I'm going to go and have a small amount of current that's going to go and flow. We know that I is equal to E over top of R. And at the very peak, we're going to go and have a voltage of 170, and if we place that 170 over top of a 20,000 ohm resistor, we are going to go and come out to a small amount of current. We'll just do that one real quick. 170 divided by 20,000, which gets us to a value of 0.0085, or what we would refer to as 8.5 milliamperes. So this equals 8.5 milliamperes. Will this be able to trigger? Well, absolutely not, because we've got certain minimum values that we have to hit before that's going to happen. And that minimum value for this is going to go and be that 10 milliamps. 8.5 is too low. Therefore, if I've got full resistance inside of here, we are never going to go and turn this SCR on. In other words, when the resistance is high in this circuit, then we are going to go and have our load shut off. But then what we can start to do is we can start to go and drop this down. If we drop this thing down to a value of 17k ohms, we can then go and recalculate. We'll take 170 volts over top of 17,000, which will, you can just divide this in your head if you take a look at it, bring us to a value of 10 milliamps. That would mean that at the point that my voltage rises and hits 170 volts over here, we are going to go and have 10 milliamps, and all we need is that brief little burst of 10 milliamps. As soon as we get that 10 milliamps that is going to hit here, then the rest of our channel is going to go into conduction. We'll be able to go and pass our AC through that. So we will then be able to go and turn this thing on, and if we take a look at this happening right over here to 170, that would mean that we would be able to carry power through that half of the cycle over there. What are we going to end up out of here? Well, if we take a look at this, we can see that we would get half power normally if we would be able to carry the whole power through, because we're losing this whole lower section, which would mean that if we go and gate this thing right now at 170 volts, then we are going to be able to go and get a quarter of the total available power as if this load were running from the AC supply. We've got a triggering angle right now. That is going to be a 90-degree triggering angle, and we're going to go and have a 90-degree conduction angle at this point. If we continue to go and drop our value from the 17K down even lower, we're going to be able to go and find smaller and smaller values. Let's say that we take this thing down to 8,500, so 8.5 kilo ohms. We can then once again go and recalculate this over here. We'll just do 8,500, and we would see that we're going to end up at a value that's going to be higher than this 10 milliamps. We should end up at a value of 20 milliamps. We'll click over to that one there. So 170 divided by 8,500 gets me to a value of 0.02, which would be 20 milliamps, which is definitely more than enough to kick it into conduction. So we know that we've got 20 milliamps that is happening right over here at the peak, but we don't know exactly when this thing is turning on yet. The only way that we can determine when this thing is turning on is we would have to start looking forward until we figure out exactly what point we reach this 10 milliamps. Well, we've got another handy formula derived from Ohm's law that will tell us that if we're looking for voltage, V is equal to I times R. What's our resistance in this circuit? Well, our resistance is currently 8.5 K ohms. And the voltage that is going to go and turn this, the current that we're going to go and have is 10 milliamps when it turns on. So what's the resultant voltage? We can just go and find that out by doing our I, 10 milliamps, times our R, 8.5 K. So 0.001 times 8,500. Put those together inside of your calculator. 8,500 times 0.01. 8,500 times 0.01, which gets us to a value of 85 volts. So wherever this reaches a point of 85 volts, we're just going to go and say that that's our 85 volts over there. That's going to be the point that this thing turns on. Well, if we are looking for what angle that is going to go and be, that means that we're going to have to go into our E instantaneous formula that we are going to go and have. You might not remember this one. This one comes out of level 2. This is what that formula looks like. That's small e, it's E instantaneous, is equal to V peak times sine theta, or whatever the angle is going to be. So if I know what the angle is and I know what my peak value of voltage is, I can figure out my instantaneous value of voltage. Unfortunately, at this point, what we're looking for is we're looking for the angle that that 85 is going to go and happen at. So what I'll do is I'll divide V peak out of both sides. So I do that. I can go and cancel those ones out, which just leaves me with sine theta. And I can get rid of sine theta by taking both sides and putting them to the inverse sine. If I do, sine to the -1 of sine, it cancels that out, which will just leave us with theta on there. And on this side here, I'm going to have to do sine to the -1 as well. I'm kind of making a mess of it down here in the corner. I'll just write it out in much prettier, which is going to be that if I have got inverse sine of my E instantaneous over top of my V peak, that is going to go and give me my angle that's going to go and happen. We can do that with this. We know what our instantaneous value of voltage is. We know that the instantaneous value of voltage that at 8.5 k ohms gives us 10 milliamps of current is going to be 85 volts. And we know what our peak is, which is going to be 170 volts. So we're just going to go and take those values and we'll put them into the calculator. Inverse sine of brackets, remember that those things are free. If you don't put them in, they're going to screw you up. E instantaneous, 85, divided by E peak, 170, which is going to get us to a value of 30 degrees that we are going to go and have. In other words, this 85 volts happens at a value of 30 degrees into there. So we've got a 30 degree firing angle, and then we would go and have the remaining, out of this 180 degrees, the remaining 150 degrees that we would have for our conduction angle. It's a pretty cool little thing that we can do here using just that variable resistor and then using that SCR. But what's not going to be a perfect one, because if I take a look, I see that the absolute max that I'm going to be able to ever put out is going to be this, where I'm going to go and have at 0 degrees, if I drop that resistance all the way down, I'm going to be able to go and carry just half of this waveform through, and then I lose that complete one because the SCR is turned off, and I carry the next one, and then the SCR is going to be turned off. If I go and increase my resistance, I'm going to be able to go and increase my resistance, and as I do so, I'm going to cut away more and more and more until eventually I'm going to go and hit my peak. Past here, if I cut away any more, if I add any more resistance, this thing will never even come on. So I'm really limited to no more than either completing what we would call half-wave rectification, which would be fully on for this rectifier, to half of that. Half of the half wave, which would be quarter wave. That's the absolute minimum that I can go and dim this thing down to. It's a bit of a pain because we can't get super low, nor can we get super high. It would be lovely if we could go and get the second half out of each of these waveforms. And it would be lovely if we could get the second half out of these waveforms, and if we could go and take these things further down, lower, so that we can get to like minimum values, etc. We can't do that with resistor. Resistor is always limited to no more than 90 degree, but we can do that when we get into our resistor capacitor triggering. First thing that we're going to do is we're going to look at that drawing, and then we're going to be sad, because when I look at it, I see that this is wrong. The big issue over here is the fact that they have taken this load and they have placed it in the wrong spot over here. I don't know who drew this. It wasn't me. We're just going to go and fix this, and we'll move it right over to the other side. It doesn't make sense because right now the load resistance is going to go and affect the triggering resistance that's going to be inside there. So we'll wipe that out. We will draw in some new lines and go over to here with our load. Drop the thing in right there. Okay. Load. There we are. Much better spell. This is what it should look like inside of your book. If it doesn't look like this, just make that correction. Taking a look at this, we've got a number of different components inside here. We do see that once again we have got a gate protection diode. That's what diode number 2 is there for. It's there to go and protect the gate of our actual SCR. We see that we've got a variable resistor, and we see that we have got another diode over here, diode 1. We're going to go and call this thing the discharge diode. Okay, that's all that it's going to be. It's a release for stored electron discharge. Okay. Well, now we get down to a favorite little component over here. You've seen these before. This thing is referred to as a capacitor. And right now you're probably being like, oh man, I hope we weren't going to cover these this year. But yes, we are going to go and cover a capacitor. What is a capacitor? A capacitor is a place where we store electrons. You guys remember Newton's laws? For every action, there is an equal and opposite type of reaction that's going to go and happen. And a capacitor really embodies that fully. I'm going to store electrons on one plate, which is going to drive electrons away from the other plate. Let's take a look at how that happens. We're going to ignore pretty much everything else that's happening on the circuit right now, and we're going to just take a look at a AC waveform. We're going to look at the positive alternation and the negative alternation. First of all, I'm going to look at this SCR. Will this SCR conduct through both alternations? Well, no, it won't, because it's a directional device. It'll only conduct when I got a positive up here and a negative down here, which would be a negative here and a positive over here. So that's the only time that's going to conduct. So we can effectively go and ignore the second half of the cycle. We're only looking at this first half of the cycle. The next thing that I'm going to go and take a look at is that my voltage is changing. My voltage is building, building, building. It hits a peak, then my voltage is dropping, dropping, dropping. But it is still always in the positive direction that it's going to be over here. If I go and take a look at I is equal to E over top of R. If I've got a small e, so it's a really, really small right now, therefore I'm going to go and have a small amount of current. And as my voltage grows, as it becomes large, then I'm going to go and have a large amount of current that's going to go and flow. We're going to see that happening through this resistor over here. But then as it drops away from being large to being small, it doesn't reverse the current. It just slows down how much current we actually have going on at any point. So don't worry too much about the fact that it's going up and then going back down, because either way it's still pushing electrons through the circuit itself. Let's go through a cycle and watch that happen and watch how that is going and giving us different values. First thing that I'm going to do over here is I'm going to go take a look at this diode, and I'm going to go and say a diode has a certain amount of breakover voltage. Nominally, we call this thing 0.7 volts that we need to break over a diode. And what about this junction over here? Well, if you go back to the very beginning of when we were starting to look at SCRs, you'll realize that this is also a PN junction. This is the N material down here, the negative. This is the P material right over here, which means that to break over that PN junction, that gate voltage, is usually going to be somewhere around the same value. So I take a look, it's about 0.7 of a volt. So for me to go and overcome the value of voltage to cause conduction through here for gate current and to cause conduction through here, I'm going to need to have 0.7 of a volt over that one plus another 0.7 of a volt over top of that one, which means that altogether we need to get about 1.4 volts. 1.4 volts is what we need to go and see at this point for us to put it into conduction. Well, where are we going to get that 1.4 volts? We're going to get that 1.4 volts off of that capacitor. I'm just going to leave that 1.4 volts up there and remove those other ones. Here's what happens. If my resistance is really high, I can only trickle a few electrons through it. So I turn my AC on. My AC starts to alternate. I get a positive up here. I get a negative over here. As soon as it's negative over here, I'm going to have electrons that are going to start traveling along here. They're not going to go through here because it's going to be blocking. Few leakage ones, but we're disregarding those. The bulk are going to be blocked. My electrons are going to start to build up on this plate over here. For every action, there is an equal and opposite reaction, which means that for every electron on that plate, I'm going to go and create a hole on the other one. And a hole is just created when the electrons over here force electrons out. These electrons are going to try to leave and go someplace. Can they get through here? Not necessarily. They will eventually, but not yet. Can they get through here? Absolutely not, because that's a negative, a cathode that is connected to a positive over here. So this thing is currently blocking during this cycle. I'll just erase that part there right now. So these electrons really have only one path that they can go to, and that's to go through this resistance. Now, if my resistance is high, it's going to be tough going for them poor little electrons. They're going to have to struggle their way through there, but they'll eventually make it through there, and then they will be able to go and travel all the way through back down to my supply over here. What happens as these electrons continue to drive in from the source and build up over here? Well, we're going to start to go and build voltage. We're distorting those orbitals. I don't know if you remember that inside there, but you're going to be distorting the orbitals, the valence electrons, and the nucleuses of the dielectric that's in between those two plates, which means that my voltage is going to start to go and build. So I'm going to go and get voltage that's going to be building. And as my voltage builds, eventually it's going to reach a point where it's going to be greater than 1.4 volts. And when my voltage gets greater than 1.4 volts, then this one is going to go into conduction, and this one is going to go into conduction as well. As soon as this one and this one go into conduction, my gate junction and this diode over here, we're going to get that little brief pulse that's going to go and happen. Remember that there's all this strain that's happening inside the dielectric. And so for a brief second, we're going to go and have a small little rush of electrons that are going to go through there. From there, back to fill holes on this side over here. But what they do is they give us our gate current, which is now going to allow us to carry the bulk current that we were looking for through our load. Up through that SCR and back out to the load itself. We've now put this thing into conduction. My voltage might continue rising. My voltage might already be on the down slope. It doesn't really matter because the electrons would either way, even if the voltage was going down, there's still voltage. It's still positive, still negative. There's still going to be electrons pushing through here. But we're going to have built a bunch of voltage onto this little cap over here. The voltage is going to go all the way through until now it hits the opposite side. It alternates. Well, once it alternates, we're going to have a couple of critical things that are going to go and happen. First of all, this positive and negative are going to go and reverse. We now get this negative and this positive. Because of that, because it's reversed, this is now going to go and shut off. We're no longer going to be in conduction on here. It actually would have shut off a little bit ahead of hitting this line because it would have dropped below the value that it needs to go and keep its holding current in place. So this is all going to be gone. We lose that set. At the same time now, we see that we've got a positive down here, and we see that we've got a negative up top over here. If I've got a positive and a negative over there, that means that this is now, erase that one as well because that one's going to be back out. This over here is going to be forward biased. And if this is forward biased, there's going to go and be a path for my electrons, which have been stored on here, to get back out. First of all, if this is positive, where do these electrons want to go? These electrons want to go over here to this positive. And if this is negative over here, this negative is full of electrons, which means that that negative that's full of electrons is going to drive a bunch of electrons through all the way to there. When it drives those electrons through there, it is going to go and fill all those holes that we just built up in the opposite direction. And because it's only a very, very small resistance that it's going to have, it's going to happen relatively quickly. We're just going to go and dump all those electrons off of there and back out to the supply, and basically we neutralize this thing. As that voltage goes back in the opposite direction, it's on the negative side and climbs back in the opposite direction, it's going to have less and less, and so it's going to actually release some of its own back as well. And in effect, what it does is it completely goes and clears off our cap, basically resets the cap so that our cap is ready for the next cycle. And that's all that's happening inside of here, is that we are going to go and once we finish that discharge cycle, so that discharge cycle happens, we would then go back into a charge cycle. And as we carry our voltage up, eventually we're going to hit the point where we will have sent enough enough electrons over here to drive enough electrons away from here that we would reach that magical 1.4-ish volts that we would need to go and send this into conduction and send our load through. The beautiful thing about this system is really I'm just looking at collecting. That's all that this capacitor is doing, is it's collecting electrons on it, and when I reach a sufficient number of collected electrons, we hit 1.4 volts, and this thing is going to go and trigger. So I can have a high amount of resistance. If my resistance is high, it's just going to be a slow collection, which means it's going to trigger late. If my resistance over here is going to be low, then I'm going to be able to dump electrons on here, push electrons away from here rapidly, which means that I'm going to be able to reach that 1.4 volts very, very quickly, which will also go and turn this diode back on. Allows us to go and achieve triggering over top of a much greater range. If we take a look at this, we see that we can get that halfway rectification, right? Because we've got only a single SCR that's inside of here, but we're going to be able to go and have at a low value of resistance. So this would be zero resistance. This one would be low resistance. At low resistance, we'll charge that cap up early, and then it's going to go and turn on and conduct through the rest of the way. By the time we get to maybe a medium value of resistance, then it's going to go and take it longer to collect electrons on there, so it's going to trigger a bit later. And if I go to a high value of resistance, it's going to be way later inside of the cycle that this thing is actually going to be able to go and trigger. It can be triggered when we're using resistor capacitor triggering. We can trigger it anywhere between 0 and 180 degrees theoretically. Practically, we're always going to be a little bit off of 0 degrees because we have to build a bit of voltage, and a little bit off of 180 degrees because we are always going to have to go and maintain that holding current. But for what we talk about, we say that we can get 0 to 180 degree triggering. It's a wonderful, cool little thing that it actually does. Last thing that we're going to talk about over here is where we've got full AC phase control, and full AC phase control is going to happen when I grab two SCRs and I put those things in a back-to-back configuration. And really we can just take a look at these and say if I've got a positive negative over here, which one of these two is going to be conducting? Well, it will be this one. That would be for the red, the positive negative. And when my AC alternates, goes to negative positive over here, it will be this one. That would go and pass current. So either one of these is going to go and pass current. We'll be able to go and pass current in the blue through in that direction. We'll be able to, on the red, pass current through in this direction over here. What we'll note is that the load sees current in both directions. This is different than what we were looking at before, where we rectified into pulsating DC, and then we used a single SCR. At that point, if you go back to that one from the previous learning tasks, you'll see that all the current was going through the load always in the same direction. In this case over here, the load sees current that's switching direction. It's going to be a true AC. They show two separate blocks that are being used as control blocks, this one and this one over here. In reality, you will have to have two, but you're going to go and set them up to usually be the same so that you can go and get an equal amount of cut off from either of your directions. It's going to look something like this that you're going to go and have over here, where the one that we had up top, the red one might be passing this waveform, and then the blue one might be passing this waveform over here. And then the triggering that we're going to go and have, that control circuit, RC hopefully, will then allow us to chop away as much as we want. This is a wonderful dimming application with the dual SCRs, because I see that if I go and give myself very, very low value of resistance, I'll be able to conduct the entire waveform here. Then I'll be able to conduct the entire waveform over here off of the other one. So we can go and get basically 100% full AC power off of this one when we're using the back-to-back. And from there, if I use RC, I can go and bring that all the way down to just a little spike that I'm going to have at the tail end of each of these. So I can go from 100% power all the way down to 0% power off of these things. If I've got a large amount of AC power, I'm going to go and use SCRs. I'm going to show you guys actually a couple of SCRs in class. They're massive industrial ones that are used for control and rectification. If it's for small things like just a little light dimmer or something like that, in a lot of cases we're going to use a different thyristor that is called the triac, which we are going to go and talk about on the next one. But if it's large amounts of current we're controlling, SCRs. We're just going to go and use them to go and clean that up. Last thing that I'm going to talk about as well is just this waveform over here. If you take a look at this waveform, it's really, really jagged. We get a high, fast wave over here, and then it drops, and then, kind of a high, fast wave over here, and then it drops. What we can do with this one came off of here, so let me just actually erase a bunch of stuff here so we can kind of draw it out a little bit better. What we could do with this, if we wanted to have a nicer looking waveform, is we could go and place an inductor inside of there so that we could go and filter. Second year, you covered a little bit about electronics and filtering, and you found out that you can go and use, capacitive filters or inductive filters. And what that would do is that would slow down my rate of rise. So this over here would kind of rise a bit slower, but then this would drop away a little bit slower as well. And it ends up as being just a more smooth waveform that is going to be seen by your load. A lot of cases, we're going to go and do that, where we're going to smooth out that waveform through the use of large inductors, or sometimes we'll call them chokes or reactors. Other times what we'll actually do is we will go and take that value. You don't think about this as 120, think about this as being like 25 kV, 25,000 volts, because we do rectify high values of voltage. We'll sometimes rectify ridiculously high values of voltage, and then we'll chop off the top part. We'll slough that through something that's going to be similar to the Zener diodes, but just a larger industrial version of that. We'll chop off the top half, and then we only have got this bottom half, which gives us a beautiful uniform DC for our DC buses around whatever the plant is that we're looking at. Bunch of really cool stuff that's in addition to what we're covering over here. Right now, we're just looking at, how do we actually go and smooth this out. These ones over here, same deal. You would do that smoothing through a choke, and what you would get is you would just get a little bit more of a smooth rise and a smooth fall and cross over to the other side. Just gives you much nicer power and fewer issues with harmonics. All right, self-test 5 is up next.